Okay, so now let's begin lecture 14, Neutron Transport, third in the series of Neutron Transport. This is the course NE402, Intermediate Nuclear Engineering, on Neutron Diffusion and Transport, and Radiation Transport and Monte Carlo Simulation. My name and telephone number, personal email, official email, and personal website. Okay, so in the previous lecture, I showed you some exact solutions for an infinite medium and a semi-infinite medium. Now let's come to, just want to show you a few exact solutions for a finite sphere with a point isotropic source. So now we're getting a bit realistic. And this was done by Erdmann and Sievert in 1968 and by Sievert and Grandjean 1979. For a sphere with a point isotropic source, they obtained an exact solution. And this is what the solution looks like. And as I said to you, that these are very useful when you use them as benchmarks, because for this we can actually use big codes, and you can also do this, which I did with you using diffusion theory. Now we're going to do this with transport theory, and then you can also do this with Monte Carlo simulation. So the same problem can be done by three different methods. So here is the rho r, and rho r is the flux at r. So this is the asymptotic value, and this is minus 1/4 pi r. Sine hyperbolic and sine hyperbolic function. And you can again see the scaling over here. The asymptotic flux is given by this integral and by this term over here. So this is the infinite medium solution. The expansion coefficient in here, E of nu naught, is given by the function g plus k times E. So quite a rigorous bit of mathematics in here, and where E of nu satisfies the Fredholm equation. Now you can see that the Fredholm and Volterra equations are integral equations which are used over here. So again, very elaborate mathematics. So the functions g and k are defined over here. So this is to get g and k, you have to solve all these equations, but it can be done. And the extrapolation distance is also found over here in terms of the Chandrasekhar edge function, which satisfies the integral equation. And I've got these in MATLAB, so I can show you the programs in a future lecture. Right now, the idea is to get a theoretical insight, to develop conceptual foundations, to understand the field. So we've come from basic nuclear physics to nuclear radiation to neutron diffusion, and this is neutron transport. So this exact solution is possible, and it is available. Now these are the values of 4 pi r square phi. Now you can see that 4 pi r square is, so the flux is neutrons per centimeter square per second. When you multiply this by centimeter square, so the flux becomes neutrons per second. Now the lower one over here is flux, and these are the finite and the infinite terms. Okay. So here you can see are the finite terms, and here you can see are the infinite terms of the above expressions. So you can see this for a strong absorber, that you can see the flux, this flux drops pretty fast. Now, if you look at a finite sphere for a C equal to, if If you look for a strong scatterer, then you'll see the opposite of what you saw above, that it rises pretty fast and a lot of scattering, so the neutrons go deep inside the medium. So this is the normalized radius going from 0 to 1. So what you see over here is is a is a little peak of the flux, coming up over there. Okay, this shows you the transport theory flux in a finite sphere for a strong absorber, in which case the flux is falling pretty fast, and for a strong scatterer, a weak absorber. So what you see over here is that this is the limiting kind of case to going towards a critical solution. So you'll see more buckling over there. Now the values of flux given in this table agree well with the results which are given in the literature in 1979. So the asymptotic flux and the, uh, the total flux. So you can see over here that as you go more into scattering, then you get values which increase. So here the values are small, they get bigger over here, and they get bigger over here. Because with more scattering, the neutrons are able to penetrate deeper into the sphere. So you can see that for a strong absorber, the flux has fallen to about half, but here the flux has increased over here. So I'll show you all these programs. You can do them yourself. Now, over here, we show the limiting case where you see that for a very strong absorber over here, you get a cosine kind of a buckling. So it's approaching the case of a multiplying system. Okay, so now those were the theoretical, the exact solutions which have a use in terms of benchmarks and in terms of showing elegant solutions to highly idealized problems. Now let's come to some practical ways by which the transport equation is used. And so we don't need to make any assumptions of infinite medium, semi-infinite medium, homogeneous half spaces. We don't need to use Laplace and Fourier transforms or Green's function. So those find very limited practical application. So what we're going to do now, there's so many methods, and I'll concentrate on two because these tell a lot of the story of the numerical methods of solving the transport equation. Now, the discrete ordinates method is the SN method. The spherical harmonics method, written as the PN method because they use the Legendre polynomials. And then later, so these were the legacy, the old methods, 60s and 70s, and later finite element, boundary element, finite volume methods were incorporated with tremendous numerical effort to extend the capabilities of deterministic codes to full 3D modeling. Now let's start with the discrete ordinates method, used extensively. Discrete ordinates. So we discretize the ordinates. We discretize the angular flux into a finite number of angles. Now, the discrete ordinates method was first used by Wick and Chandrasekhar for, as I mentioned before, for radiative transfer analysis in stellar atmospheres. And there's a very comprehensive review of the method, the whole chapter in Bell and Gladstone, 1952. So it's a very old fat book, which I've got two of because when I was a student, I bought two copies. I thought in case I lose one, because I was traveling, moving from England to America to Pakistan. So I thought if I lose one of these, so I should, so I've kept this book. I've kept a few books like Lamarche, Bell and Gladstone, and some other less well-known nuclear engineering books. I've kept them since the 1970s. And I have the old version of the Nuclear Engineering Handbook by Etherington, 1958. So these books I've always kept with me, and believe it or not, I keep referring to them. I keep going back to them to try to understand more and more. So, and every time there's something new to learn. So the first use of the discrete ordinates method that I found was by Vic and Chandrasekhar. And then there's a lot of very good work by Carlson in 1968, and the book by Carlson and Lathrop, and they developed codes on this. It was called ANISN, ANISN, anisotropic SN method, which I did use in the early days, but then I shifted to 3D codes and all. So ANISN was something which students were taught at in the master's program. I don't know how much of it is used now, but I think many of us got into numerical methods by using ANISN. Then, of course, DOT came, the two-dimensional discrete ordinates transport, then TORT and TART and one-DAN. So basically, depending on the lab which developed them. So these are extensively used codes, and I'm sure that now they must have gone to a very high level of sophistication. But I did not follow this. I went into Monte Carlo simulation. So, but I'm sure that this has really gone to a very high level of sophistication now. Okay, so essentially what happens in the discrete ordinates method is that the solid angle omega is discretized into a quadrature scheme. And they use 2, 4, 8, 16, 32 divisions. So, and so you can have more and more elements to define complex geometry where you want to get information. So the mu interval, which I told you goes from -1 to 1, back scattering to full forward scattering. So 0 degrees scattering to 180 degrees scattering, because that's the cosine of 0 is +1, the cosine of 180 is -1. The cosine of 90 is 0, so that's a full angle. So the mu interval is divided into n intervals, and so the left endpoint is mu naught equal to -1, the right endpoint is mu n is equal to 1, and in between you've got values. So for example, if I say I'm solving in the S4 approximation, so that means that I've got 5 values of mu from between -1 and 1. So I've got -1, -0.5, 0, 0.5, and 1. Now, in the limit of mu j -1 to mu j, the flux you can approximate by the flux, angular flux r mu, you can obtain from r mu j plus r mu j -1. So the approximation is then substituted in the transport equation, and after integration over mu, so you get n equations. And to obtain the final equations, an additional equation is required for mu equal to -1. So very exhaustive considerations on this are by Clark and Hansen and by Bell and Glasgow. Now, just to show you that in the transport equation, the integral term is written as a finite sum of the quadratures, so in the discrete directions. So this is converted into the discretized angular flux multiplied by certain weights. Now these weights you can see are over here. So for example, this is the omega I and these are the mu I. Now I remember once I tried deriving these, and I think I got the mu1 and mu2s. So maybe it's a worthwhile effort for students now to see how you get these quadratures. So, and before you do this, better to evaluate integrals using the Gaussian quadrature. So these are the discretized angles, and these are the discretized weights. So that's how you convert from a continuous problem to a discrete problem. The higher the order of Sn, the higher the value of n, the better your answer is expected to be. So in the transport equation, the continuous equation that we had with the integral term over here, now gets it gets converted to a discretized angular flux over here. It is still an equation that has a d by dz term sitting over here. So you need to have a finite difference scheme over here, and you need to take your points such that if you don't have a straight boundary, then you can use a variable grid over here to match your boundary. So this is what the SN method was, that you just discretize in terms of angles. So, and the higher the order of the method, the better your results are supposed to be at the cost of greater computational effort. Now let's look at the spherical harmonics method. The spherical harmonics method says that the angular flux is expanded in terms of, see separability over here, that the space function is written over here and the angular function is written over here. So these are the Legendre polynomials and these are the moments. Now, if I can just show you what they look like, or let's go through this a little bit first. So any function can be expanded in terms of Legendre polynomials. And you can write the moments of this function. So the moments are the phi m, the mth moment, is the angular flux multiplied by the mth Legendre polynomial, and you can expand that. Now they have what is called orthogonality. So in other words, if I were to multiply this by Pn of mu, so there'll be an integral of Pn, Pm mu, d mu between -1 and 1, and you'll see that gives you 2 delta Nm over 2n plus 1. So it gives you a very compact expression. It simplifies the equations, the governing equations, and it makes things much easier for you to do. Now, let me take you to a little bit introduction on the Legendre polynomials. So let's take a look over here, that taking you to Wikipedia. And so these are the first six Legendre polynomials. But first, let me show you what they look like. So this is the orthogonality condition I was telling you, that if n is equal to m, then it gives you something, otherwise it gives you nothing. Okay, so that's the orthogonality condition. Now here's you can define them by a generating function. You can define them by Legendre's differential equation. So these are some of the properties. Orthonormality, that Pn, Pm, the mth order multiplied by the nth order. So it gives you 2 delta Mn over 2m plus 1, or 2n plus 1, where delta is the Kronecker delta. It's equal to 1 or 0. If m is equal to n, then the delta Mn is equal to 1, otherwise it's 0. Okay, so once you use these functions, you can get the moments. Now, the 0th moment of the angular flux is the scalar flux, and the first moment would give you the x times phi 1, or mu times phi 1. So now these are the expressions, but I just want to show you the shape of the Legendre polynomials. Okay, so the first few Legendre polynomials, P0 is 1, P0 of x is 1, P1 of x is x, that half 3x squared minus 1. So as a student, I think I would often remember as far as the third. So that's the 0th, first, second, third. Yes, I used to keep till the third over here. So half 3x squared minus 1 and half 5x cubed minus 3x. The higher ones I wouldn't say that you memorize because they're usually given if they're required to be used. So this is what Legendre polynomials look like. Now the green one is P0, so P0 is 1. This one, the bluish green one, the turquoise one, is so you can see that it's a straight line going from -1 to 1 1. So this is P1 of x is x. Now P2 of x is a half of 3x squared minus 1. And that's the dark blue. So the dark blue goes like this, and it goes up, it's parabolic. So then you've got P3, P4, P5. So what are the applications of Legendre polynomials? Applications are that you can use them for separability, and you can see over here what they are. So you can use them for when you assume separability. Then you can use the orthogonality and orthonormality conditions, and you can simplify the thing. You can generate moments. Remember, from moments you can reconstruct a continuous function. Okay, so now let's go back over here to the spherical harmonics method. So we seek solutions for the angular flux in terms of the moments of the spatial flux plus moments of the Legendre polynomials. Now this method is called the PN method, and the angles are written in terms of spherical harmonic functions, which are orthogonal in the range -1 to 1, where mu equal to cosine theta. So let's continue over here. So you can see that the I showed you the first few spherical harmonics, and this is the condition, orthogonality condition, Kronecker delta function. So the zeroth moment is the scalar flux. The first moment, the significance of the first moment, now look at this. P1 of mu is mu. So if I multiply by the first moment, what do I get? I get the current, J. So we can think of an equivalence between a P1 transport formulation and the diffusion equation. If we've got the flux, we've got the current. Okay, so now in the transport, in the one-speed equation, if you write for flux the position and the angle dependence, and you know, put them all down, so you get 439. Now you can also use recurrence relations for spherical harmonics. As you can see that the Legendre polynomials, the m is connected to one above it and one below it. And you can also use the orthogonality, so you get a differential equation which connects phi n with phi n plus 1 and phi n minus 1. So again, you need to do a finite difference over here, and so you can solve, you can have a matrix, you can assume, you can start from an initial condition, and you can apply the boundary conditions, so you can converge to the solution. So the PN approximation is where you throw away the higher terms. So phi d phi by dx or phi n plus 1, if you put that to 0, then you get what is called the PN approximation. Now again, as for the Sn case, the higher the n is, the better your answer will be. For the case of x not equal to 0, i.e. when you're far away from the source, so equation 412, because the previous one is a set of homogeneous, no, I'm sorry, it is this one. So it's a set of homogeneous first order ordinary differential equations with constant coefficients. So now the solution in the P1 approximation gives you that the flux is, now 1 minus C is again cropping up. So C is sigma S over sigma T if it's a weak absorber. So you can see over here that the answer is pretty much similar to what we had in the diffusion case. So the Sn and Pn are very widely used numerical methods in the transport equation, and the P1 is similar to diffusion equation with flux and current. Now there are other deterministic methods such as the finite element method, uh, which is based on variational calculus. So, uh, and then there's a finite volume method, the boundary element method. So transport theory in the P1 approximation. So remember that the quantities flux and current were the zeroth and the first moment. So let's see what happens to the equation. So this is phi 1 and this is phi naught. So phi naught is our previous in diffusion, we called it d phi by dx. Now this is the current J. So from here you can see that J is equal to minus d phi by dx. So if you combine these two equations, the current and the flux equation, so what you get the familiar diffusion equation. So we have recovered from here for the case of a delta source, and you can see that this is again sigma s over t. So this is sigma a, because sigma t minus sigma s is sigma a. So we've got the sigma a over here. Downstairs we've got a sigma t. So sigma t you can multiply quite conveniently, and you can see that the P1 transport equation is similar to the diffusion equation. So the solution is also the same. So phi x is L over 2d e to the minus x over L. Okay, so you can see that the diffusion length is L equal to 1 over square root of 3 times 1 minus c. So let's see what are the applications of transport theory. Now, the neutron diffusion equation is based on Poisson's equation. It is mathematically much simpler than the integral differential transport equation, and hence the diffusion model is used for simple problems. Even then, numerical solutions are required for large problems such as whole core reactor design. In the multigroup form, the diffusion equation is used to obtain first estimates and can serve as a useful step for providing guesses to full transport calculations. The limitation of diffusion equation is near sources and boundaries, where the angular flux requires detailed consideration. So in that sense, detailed consideration is provided in the discrete ordinance and spherical harmonics method. So these methods, the transport numerical methods, are much better than diffusion theory, because diffusion doesn't hold valid near the source and near boundaries. Now let's look at a number of problems that we are now in a position to solve. So the first problem I've given you is to compare the neutron flux obtained by transport theory, if you go back in this lecture, and that obtained by diffusion theory in a finite sphere with a point isotropic source at its center. Plot the flux for a source of 10 to the 7 neutrons per second. So I think this is a very important exercise for you to compare the diffusion and transport fluxes for a finite sphere with a point isotropic source at its center, and plot the flux for a source of 10 to the 7 neutrons per second. The second question is on the spherical part of it, and I was asked for an application on Godiva. So Godiva was a bare sphere, 94% U235, and I think in one of the previous lectures I told you that its critical radius was of a bare sphere. Godiva is 8.710 centimeters, and its mass is close to 50 kilograms. And you saw that with the reflector, the size and mass are significantly decreased. Okay, so so this is essentially it, and I'll stop over here. So so these were the 3 lectures on transport theory. So now you have completed diffusion, as well as transport, the basic foundations, the basic concepts. Of course, there's much more than what we have covered over here. In fact, there's no end to it. But this gives you the basic building blocks to develop a good understanding. And with a good understanding, we'll be able to solve many problems. And those which I have not, the theory which I have not considered with you, well, that you can extend these things and look here and there to find where things are, because you must know where the things are. You don't have to memorize everything, and you don't have to learn everything, but you must also be able to, you must also learn how to use equations and data.